right, good morning, everyone. Happy Saturday. Made it to the weekend, and so I woke up at my usual crack of dawn. I'm up way too early. I never stay up for Advent of Code problems because I'm usually up by 4:30 in the morning. Usually I go running, but it's kind of icky, rainy out. But I've had my coffee, had my breakfast, finished the crossword puzzle, and so why not do another walkthrough of another one of these Advent of Code solutions? So that's what we'll do. So this one was kind of a cool problem, and yeah. So let's kind of jump in and looking at the problem. So again, you should check these out. I'm not going to go through the whole story because you should be just reading them through, but the gist is, we're now at the point that we want to get our seat on a plane for our travels. And the way it works is, it says here the airline uses binary space partitioning in order to figure where your seat is. And you're going to get a seat descriptor kind of like this, FB, BBB, FF, RLR. And so that's going to, so the FBFBB is front, back, back, front, etc. And RLR, right, left, right. And so it says the first 7 characters of the string specify the row and the rest the column. And then it goes on to say even more. You'll have 7, and they go from 0, and the rows are 128 rows from 0 to 127. And so, this is good. Now, again, I try to look at this from a teacher point of view rather than just solving it, and I think this is a nice problem for a computer science class, a CS0 or a CS1 or an APCSA being a CS1, because you see that 0 to 127, 7 bits base 2 binary, there's going to be something there, you already should see that. Now the students might not see that immediately, so you want to kind of set the stage for that. So each letter tells you whether it's front or back. So front is the lower range, back is the higher range. And, so here you'll see that, so you basically, if you look at the FBF, whatever, you start with your 127. And if you're going to be in the lower half, the front, it's a lower number. So you subtract the 64 from that, and now you're looking at 0 to 63. And then with the B, you're looking at the upper half, so you don't subtract anything. And then the next one, we subtract a 32. So we clearly have these powers of 2. And so, and then that gives us to the row 44 if we figure it out. Then for the 8 columns, we've got, so for the rest, for the seat number, for the column, it's the next 3 digits, right, left, right, but it works the same way, and it steps you through it here. So read through the question if you haven't already. Think about it a little bit, and let's just start talking through this. So to start with, let's make a seat just for testing. And that's going to be our seat. And so we can look at it, FBFBB, and I'm just double checking it, FBFBB, FFRLR. Okay, now what struck me at this is like, well, this is going to be binary, but what we're going to need on there, it's going to be a base 2 type figuring it out. But if we look at it, so this is going to be like, oh, should I subtract? Well, the first thing I think of it is the front and the back, the 2 parts are separate. So let's make the row will be the front of it, and the column will be drop 7 from the seat. And so our row is going to be front, back, back, front. And the column is going to be right, left, right. So we've now separated these. Now, and if you're not a Clojure person, God, I can't hit keys. The /F/B, that's how it represents characters, because it converts that into a sequence. internally, so it's no longer a string when we take the 7 from it. And so when we're looking at this, FBF, BBFF, if we're thinking about this, if we look here at the F, the first F, that's going to be, let me just look at the row here. If we look at the row here, this is going to mean 64. We're going to want to take away 64 from a 127. We're going to want to take away nothing from this one. So that'll be not, we're not going to take away the 32. Then we're going to take away 16, or then nothing, then 2, and then 1. So if you think about it, this is a binary number, a base 2 number. And I was thinking about it, that eventually we're going to have to, like, we could convert this into ones and zeros. Like we could convert this into like this could be a number like 10110011 as a base 2 number, because that really is what it is. But then we'd still have to convert it into an actual, go from that into whatever the numeric version is. We couldn't just type this in. Actually, there might be a way of doing it in Clojure. I don't know offhand. The other thing, though, is it's not actually that number. This was something that I'll talk about in a minute, which is, but it's the reverse. So I was being stupid. Because here, this is the bigger numbers. This is 0, the 1s, or rather, these are the 1s, the 2s, the 4, the 8, the 16, the 32s, and the 64s. So it's in the wrong direction. So what I started thinking is, okay, well, or rather, I started thinking kind of a stupid way. I was like, well, I'm going to want to go over this kind of based on what its position is. So I'm going to use in Clojure something called map indexed. And I'll just write a function f here, which takes 2 arguments, the index and the arg. And we're just going to print out, or not print out, but we'll just return it as a list, def function. We're going to map index on this function. Let's do it with the row. And so you'll see we get 0, 1, 2, 3, 4, 5, 6, etc. And what we're going to do is we're going to have to calculate that f is not actually going to be the 0. That actually is going to be, I've got to calculate, 2 to the 7, and then the next one 2 to the 6, 2 to the 5th, and I had to subtract it. I'm like, I'm really, but they're in the reverse order. This f is the 1s, and this f is the 64 place. This r is the 1s, and this r is the 4 places. So we're going to reverse these. So now it's the same deal, but it's going to be in reverse. But we'll notice that what we have is that we have FF at the beginning, and that's the FF at the end of the row. And then we have BF, which is at the beginning. So really, if we have, if we calculate is that the ordering for? Repeat 6 times 2. There we go. If we calculate the power of 2 to the 6, we just repeat 2 6 times and multiply them all together. We reduce it, and I talked about reduce in the previous video. That's going to give us the 64 that we want to take out from this one. And we can do the same thing for this one here in the or rather for, well, not for this one. This is going to be a 0, a 0. Then this one in the 4th, it's going to be the 16 we want to take out, but we don't want to do it for the b's. So we're going to have a little function in here, a little, well, let's make some stuff. Let's make the takeout, and the takeout is just going to be reduce with the time, repeat. And do I want to do it I times or one more than I? Because yeah, I'll do one more than I, because I'll start at 0, so it's got to be one more than I. And so that's going to be how much we're going to take out. But we don't always want to take out. We want to take out if it's an F. And is it an F? Let me look at the problem, which I haven't up on my screen still. I'm just not broadcasting it. If it's an F or if it's an L, we want to take out some of the value. So let's see. So, and actually we don't even have to increment I, because we can just take this, we'll just treat it like one less. So this should work. So what we're going to do here is we're going to say if or equals, if the arg equals the capital L, or the arg equals the capital, did I say F? Then we're going to want to return the takeout. Otherwise, we don't want to take out anything. So now let's map that on the row, and basically it looks here, we want to take out the 64, we don't want to take out the 32, but then we're going to take out 16, don't take out, don't take out, take out, take out. So now if we actually, to finish this off, all we have to do is reduce with the minus and start this out on a value of 127. And that gives us a value of 44, which is what we're looking for. So that, and 127 is our starting 0 to 127 seat. And what the reduce does, I showed you the reduce. I told you how reduce, like if we reduce plus 10, 100, and 1,000, if I got, let me make it a vector. It'll be 10 plus 100 or plus 100 plus 1,000 here. It'll add the first to the next. But if I give it a starting number, it'll start by 55, 5 plus 10, then plus 100 plus 1,000. So this is going to do all of those subtractions, but it's going to do it starting off the 127. So now we can really just pretty easily do this part one. So let's get our seat, get seat number, and it's going to take a seat string. And from the seat string, we're going to say, let's let our row be reverse take 7 from the seat string. And the column is going to be reverse take 7 from the seat string. And I'm just going to actually call them row and column string. And so now we've got our row string and our column string. So all we have to do is we're going to, well, now we're going to make the actual row is going to be, what did we say it was going to be? Map index, we'll just do it one step at a time. Map indexed using our function f that we wrote up there and on our row string. And our column is going to be map indexed f on our column string. And just for the time being, we'll just return row and column in this way. Got an error because that's a defend, not a def. And now let's just check it out. Get seat number of our seat And this doesn't look quite right. 1, 2, 1, 2, 0, 0, 16, 0, 64 is right. But the column string, because I have to drop 7 from this, 0, 2, 0. And I think that is right. So anyway, actually, that is not right. Did I have this wrong? Should it be L or should it be R? Let's see, map indexed F, and the column string should be for this, well, it should be RLR. Oh, well, let's see if it works. Okay. Well, actually, no, let's test it. Let's test it. Map index column seat. Not seat, column. And then we want to, and am I doing the reverse up there? Yes, I am. So we then want to reduce -7. Oh, that's 5. Yeah, we're fine on that. Okay. So so basically, that's that looks good. What we want to do is we want to do that reduce on each of them. And for the row, we know it's reduce minus with 127. And for the column, it's reduce minus and 7. That looks good. And then it says for our final answer, what we want to do is we want to return the value of, we want to add together 8 times the row plus the column. And that's our seat. So it's pretty straightforward. Once you see that binary relationship, it becomes a pretty straightforward problem. And if you don't see that, you could kind of mechanically, like if I'm doing this in a Python type language, I could see me just like looping over the string and keeping track of variables. But it's pretty straightforward if you look at it this way. But let's make sure we're actually 100% correct. Let's do our usual. I guess we don't need these for now, but we're going to take day 5 Clojure, put it through IS resource, put it through slurp, and put it through split lines. Data. That looks good. Let's put it into data because that's what we always put it into. And so now what we can do is we can say, define our seats to be, let's map get, let me change this to seat number. Let me get the spelling correctly. Get seat number onto our data. And that should be everything. Now, they gave us a bunch of, actually, we could do a little test on our, they gave us in the problem like 3 samples and we could test that, but I'm pretty confident this is going to be okay. So let's look at seats. Okay, and we want to have the maximum, and so in Clojure, we can just do that by applying the max function onto seats. And we do have a problem here. That is not quite right. The highest seat ID on, oh, no, that's not quite correct. That could be right. That actually is correct. Sorry, I was looking at the data, the demo data again, and that actually is correct. So we are good with that. And let's go back to, whoops, hit the wrong key there. I see that. Okay, good. That should be okay now. I see that the keystroke was being intercepted by Emacs that will control my view. So we see 996. Now, the next part of this is actually pretty straightforward, and there are a couple of ways of doing this, or a few ways of doing this. What they want now is, for the second part, they want to see where your seat is. And so your seat is going to be missing. It's not going to be in the set. Now, you know how the plane works is the seats are, for the most part, going to be consecutive. And it says here that, the ones on the ends don't have neighbors, but all of the others do have neighbors. And your seat is going to be the one seat with nobody on the left and nobody on the right, or not left and right, because they go to different rows, but they say here ID +1 and ID -1. So one way of doing this is something like this. We could say, let's turn our seats into a set of seats. And so now, it's kind of like, I'm thinking hash table lookups. And actually, let me go back to the Emacs screen. So I just, fortunately, I caught this early enough. And so it's now a set of seats. So it'll look, it looks kind of the same, but it's a set. And so now what we want to do is we want to go and see for every seat. So let's so now we have the lowest seat at 21 and the highest seat as 996. So now we have all of our seats, so we can just do a simple test. We can basically say, let's check to see if a seat is empty. And that's going to be quite simply if your seat doesn't exist, it's not in our set. But that's not enough, because in addition to that, the +1, the increment of the seat, and the -1 do have to be in the set. So do I have a mistake in here? And this actually should be so now we can easily check to see if a seat, is valid or not. It's basically, there has to be one to the left, there has to be one to the right. And so, for example, if we check to see if a seat is empty, well, I mean, most of the seats won't be empty, just the edges. So let's just check this out. And so we can filter is empty. Let's do it using the right semantics. We're going to pass in the seat set and whatever the argument is, and that's going to be from a range of, let's just say inc, the lowest seat, and dec, the highest seat, because it can't be the lowest or the highest seat. And it turns out that 671 is the seat in question. That's the one we want, and we're pretty much done. So there's another way we can do this as well, and this is the way I originally did it. And and I kind of like these set lookup things, or hash table lookups in other languages, because they're fast and they're pretty easy, they're pretty straightforward. And one of the things here is, we know this is a plane. Planes are not that big. You're not going to have like 20 billion seats, and have these huge issues going through things. So you can really do this a lot of ways. So another thing you can do in Clojure is we could also kind of do this kind of more of a stream-based thing. So for example, Clojure has this thing called partition. And so if I look at partition of my seats by threes, it's going to take, if you look, well, it's kind of hard to see here. Let's say we sort the seats, because that's what we're going to have to anyway. You'll see here it's 21, 22, 23, 22, 23, 24, 23, 24, 25, 25, 26, 27. It's grouping them by threes. And so what we can do is we can say, let's filter these seats based on the function, and we'll destructure ABC, and basically not equals inc A, B, and dec C. So we're going to basically see, we're going to take things out if A plus 1 is not the same as B, is not the same as C minus 1. So if the neighbors are all of the same values, and if we run this, we have a mistake. Do I have that right? I thought I had that right. Not equals, not equals. And notice that it's 69, 669, 670, 672, 670, 672, 673. And if we look here, 671 is the missing seat, and we can just see from inspection here that 671 is indeed the missing seat. And we could clean this up a little bit more, but that's the gist of it. So this is kind of a cool problem. There are a couple of ways of doing it. There are more than a couple of ways of doing it. I liked it a lot. I hope you enjoyed this, and have a great rest of time till we see each other again.